Today we're going to be talking about chemical formulas, which consist of molecular formulas, empirical formulas, and ionic formulas. So the first two we're going to talk about is molecular formula and empirical formula. But just to start off, the chemical formulas, they basically tell you what a molecule consists of, what atoms it consists of. So say for example, H2O. This is basically saying it's like a mole ratio for the compound. So it's saying in this compound, H2O, which is water, there are 2 hydrogen atoms per oxygen atom. Or you can think of it as 2 hydrogen moles per oxygen moles. So this right here is a molecular formula. Another example is we can say CH4. Okay, another chemical formula or molecular formula, which means there's 1 carbon atom per 4 hydrogen atoms, all bound together in some sort of structure. Then another one can be, say we have C2H6. Okay, so this again is a molecular formula, which is basically saying we have 6 carbon atoms per, I'm sorry, 6 hydrogen atoms per 2 carbon atoms, all put together making some sort of structure. All 3 of these are molecular formulas, but we're going to talk about empirical formulas. Empirical formulas is the same exact thing. All you have to do is reduce it. So remember, like I said, the molecular formulas are basically mole ratios. 2 hydrogen moles per 1 oxygen mole. 1 carbon mole per 4 hydrogen moles. 2 carbons per 6 hydrogens. So for empirical, you're just basically simplifying that ratio. So we can, let me do this. So like a ratio, so this ratio is 2 to 1. This ratio is 1 to 4. No, that looks bad. There we go. And this ratio is 2 to 6. Okay, so we'll start off on the one on the right here. So, oh, did not mean to do that. Okay, it's okay. It meant to be a laser pointer. Okay, so this one right here, C2H6. The ratio is 2 carbon atoms per 6 hydrogen atoms. So if we're going to reduce that, 2 can reduce down to 1, and then the 6 can reduce down to 3. So it becomes CH3. Alright? How about these two? CH4. We have 1 to 4. Can that be reduced any further? Nope, so stays 1 to 4. So therefore it stays CH4. And then this one stays exactly the same because you can't reduce 2 to 1 any further. So it stays H2O. So the red is the empirical formula. The black is the molecular formula. The molecular formula, once again taking it from the beginning, is basically just a ratio between the moles or atoms for a compound. There's 2 hydrogen atoms per 1 oxygen atom. There's 1 carbon atom per 4 hydrogen atoms. And then there's 2 carbon atoms per 6 hydrogen atoms in the structure. That is the molecular formula. The empirical formula is the same exact thing, you just reduce the ratios. So 2 to 1 can't be reduced any further. So the molecular formula is actually the same exact thing as the empirical formula because the molecular formula is already reduced as far as it can be. Same with this one as well. But on this one, on the other hand, C2H6, we can reduce the C2H6 down to CH3. So this right here is the empirical formula is different from the molecular formula. So that's all there is to molecular formulas and empirical formulas. And just to make sure we can do another practice. So let's say we have butane. I like butane. So that right there is the that is the molecular formula. So that can be reduced. Well, let's do. It's hard to write with this. Molecular formula. So this can be reduced to the empirical formula, which is going to be, let me change to red. It's going to be, let's see, 4 to 10 ratio, so that can be reduced down to C2H5. And of course, they have to stay as whole numbers. So this is as far as we can reduce the C4H10 down to, without breaking into fractions, is C2H5. That cannot be reduced any further. So this is the empirical formula. Pretty easy, right? Just basically simplifying stuff, just basic math. Alright, so that is molecular formula and empirical formula. Let's check out ionic formula. Okay, so now for ionic formulas. Ionic formula is specific for elements or ions which come together. So for example, if we have Na plus and Cl minus, which is basically just table salt. So when the sodium comes together with the chloride, they actually form this very complex crystal structure, but they do so in such a way that their charges cancel out. So the overall ratio will be so that it becomes electronically neutral. So ionic formulas are probably the most complicated, but I'm telling you, they're actually pretty easy. They're not hard at all. So if you get, what's going to happen is you're going to get two ions, and you're going to have to figure out what the ionic formula is. So say I give you sodium and chloride. Now all you have to do is pair them up in a certain ratio so that they're electronically neutral, or basically their charges cancel out. So you look at sodium, has a +1 charge. You look at chloride, it has a -1 charge. So this is +1, this is -1. If we put 1 sodium with 1 chloride, the overall charge will be neutral. So the simple ionic formula is just NaCl. Pretty easy. That one is. Okay, let's try and bump it up a level. Alright, let's say we have, instead of sodium, say we have Mg, magnesium 2+, and we'll do chloride again. Okay, so this one's a little harder. Now we have magnesium 2+ and chloride, which has a negative charge. So we're going to have at least 1 magnesium. We can't have half of magnesium. So we know magnesium is going to be 2+, but the chloride is only -1. So we're going to need twice the amount of the chlorides in order to cancel out the charge of the magnesium. So once again, we have 1 magnesium, and then for the chlorides, we're going to need 2 of them. Does that make sense? So the magnesium is a 2+, and the chloride only has a negative charge. But if we have 2 chlorides, the overall charge will be -2. So we have magnesium 2. Oh, let me erase that. Magnesium 2+, and then the chloride negative, and then the chloride negative. So the overall charge is going to be equal to 0. And so it's MgCl2. Okay? Now, there's a certain strategy that you can use, which we'll do on the next one. So let me box off the area right here. So the next one we'll do something a little more complicated. Alright, let's say we have aluminum 3+, and you have to put it with oxygen 2-. Now, like I said, there's a certain strategy that you can use, which we could have used on the previous 2 ones, but I just want to explain the concept behind it of you trying to cancel out the charges. But this one takes a little more work than the rest of them. But what you can do is this. So what we're going to do is we're going to write the ionic formula that we know we're going to have so far. So we know it's going to be ALO, and there's going to be some subscript that goes right there. Okay, well here's the trick. Make sure you pay attention, because you won't want to rewind this. So you take the charge that's on the aluminum right there, and we're going to put that. Actually, it's not really the charge. Let me take that back. You're going to take the magnitude of the charge. So not the 3 plus, but that 3. It's plus 3, so you're going to take 3, and you're going to put it as a subscript right there. Alright? And then for the other one, okay, well, let's write that. So 3. Then you're going to take the charge on the oxygen, the 2, and you're going to put it right there. 2. And there you go. That's your answer. But I know I just showed you that, but let me show you how it makes sense. So aluminum 2, oxygen 3. I'm telling you, that is the ionic compound. Let's see if it makes sense. So you have 2 aluminums. Aluminum 3 plus with the 3 plus charge each. So that equals a total of plus 6. So if this is really the ionic compound or ionic formula, the oxygen should have a -3 or -6 charge. So you have 3 -2 oxygens for A. So 3 times -2 equals -6. Plus 6 will cancel out with -6, and there you go. So this whole strategy or this method that I showed you can be used when you're trying to figure out every ionic compound. So the sodium, that was pretty easy because it's 1 and 1, so it goes 1 and 1. Magnesium, I mean, you can kind of do that in your head. Plus 2, so you got to double the chlorides. But see how it makes sense? You see the 2, it went down right here. And then -1, which is just a 1, it went down right here. The 1 went right there. The 1 went right there. So this works for making every ionic compound. Okay, so I have about 3 minutes left, and I wanted to elaborate on a certain issue I always came across while tutoring people these ionic formulas, or coming up with these ionic formulas. So we're going to do these two, find the ionic formulas for these two real quick. So we look at these. What's special about these two is that they deal with these polyatomic ions, which you probably have to memorize in your first general chemistry course. So the polyatomic ions, which polyatomic meaning we have multiple atoms in this ion. So we have 1 phosphorus and 4 oxygens. But the important thing is that you treat it as one entity, one unit, with a -3 charge, because that's what the important thing is. So when we're coming up using the same method, this 2 will be the subscript for right here, and this 3 will be the subscript for right here. So we get C3PO4, and we put this 2 here. The special thing is, remember, we need 2 PO4s. So therefore we have to put parentheses right there. And these parentheses indicate that the 2 applies to everything in the parentheses. If we didn't have the parentheses there, it would look like this. 42 oxygens. That's not right. So the parentheses shows what exactly this subscript carries on to. And you cannot use the distributive property and come up with something like this, because that as well is not correct. Because the 2 is saying you have 2 individual PO4s. If this, on the other hand, is saying you have P2O8, this is more specific on what the structure would look like as compared to this. So this is the correct way to do it. Now we look at the other one. This will be C2SO4, 2 parentheses, but you can simplify it down to CSO4, because ionic formulas are always the empirical formula of it. And also, if you just think about it intuitively, the whole point is for it to cancel out to be electronically neutral, and it only take 1 calcium will cancel out 1 sulfate, so you just need 1 to 1. So be careful when you're using that method that I showed you before, to make sure that you simplify it as far as you can afterwards.